when you drop an object, it falls. When you do this in air, sometimes there's aerodynamic drag that will make denser objects fall faster because the drag is less significant compared to less dense objects like feathers that have high surface area, high drag, and they'll fall a lot slower. But if you take away the air so that there's no pesky air getting in the way, slowing you down, and you just drop things in a vacuum, they're going to fall at the same rate. For example, on the moon, there's no atmosphere, there's no aerodynamic drag, so dropping a bowling ball and a feather at the same time, they will fall at the same rate. And these are governed by our constant acceleration equations based on the acceleration due to whatever body you're nearby. So if you're on the moon, it would be the local gravity there at the moon. Here on Earth, it would be the gravitational acceleration at Earth. And these are the equations then. So these are constant acceleration equations, but written in such a way where you're assuming that my coordinate is positive going up, and because gravity is pulling downward, that's why my final velocity is equal to my initial velocity, where that's positive going up, minus gt, where that g is the gravitational acceleration of 9.8 meters per second squared. And that's the magnitude, and the negative is just saying that it's opposite that direction. So you can rewrite this with whatever sign convention you'd prefer, but that's what these are. These are constant acceleration equations that are valid for free fall, neglecting aerodynamic drag. Neglecting drag. So if you can't neglect drag, then these won't be valid. So dropping a feather, it's not going to behave this if there's air around. But dropping a feather in a vacuum, it will behave this. And there's a fun video here from the BBC that shows a bowling ball and some feathers being dropped in a very large vacuum chamber. And you can see they drop at the same rate.